So this is Nick Sullivan, and his interesting fact is that he was once an extra in a Bollywood movie called The Love Story of a Spy, which is ironically the name of his talk.
That's right, yeah. Love Story of a Spy. Okay, well, hi everybody, I'm Nick. I work at a company called CloudFlare, and I work on Go and crypto and security engineering type stuff. So just as a raise of hands, who here is familiar with cryptography from a development standpoint? Okay, so some people tentatively raising their hands. It's a little scary topic, but who here is familiar with Go's cryptography part of the standard library? So actually quite a few. Okay, so this is good. I don't really have a lot really new to say, but I kind of want to tell a story about CloudFlare and how this piece of code, the crypto standard library, has kind of interacted and grown with the projects we've had at the company, and you know, how changes there have influenced us and how our changes have influenced that library. So first of all, just as a reminder, what does the Go crypto library do? Well, it really does just the very basics that you need to do cryptography for the protocols that you use on the web. And specifically, it builds everything that you need to do TLS, which is the successor to SSL. This is the algorithm that's used for transport security. It also, to do TLS, you need to know how to handle certificates. And this is this really messy thing called X509 that we all love. But in any case, these are kind of the basics that are implemented to do, you know, the right strong version of TLS. And looking at the code, I decided yesterday, hey, who wrote this? And well, this is ordered by lines of code. This is really Adam Langley's work mostly. And if you can see down here, there are some names in orange. Those are the Cloudflare employees. You can kind of zoom in there. And then there's me right down there at the bottom. So I didn't really write a lot of this code, but I've worked with it a lot. And if you look at kind of the history of Go, and this is a timeline that I built, and overlap it with what CloudFlare has been doing, it's really, we're early adopters in a way. We started several projects right around the beginning of 1.0 when we had the stability promise. And I'm going to talk specifically about 4 of these projects. Railgun, CFSSL, RRDNS, and then a more recent one called Go Keyless. And you may ask, why did Cloudflare start using Go? And really, there's one reason. I don't know if you guys recognize this guy, John Graham-Cumming, but or the infamous JGC, we call him. But yeah, he actually started Go at Cloudflare kind of in secret. There was a project called Railgun, which is really intended to speed up caching for Cloudflare CDN. And it does so by smart differential changes. Basically, if you have a static asset that has only slight changes, you can send deltas and really, you know, break the speed of light, as they say. And we started it right around the time of Go 1.0. And this backend connection, it's supposed to be encrypted, right? If we're good citizens of the internet, we encrypt everything for you. And we encrypt it with TLS, and back in this day, it was actually a huge CPU hog. And so what JGC did was this kind of amazing hack where using Make and CGO added OpenSSL into Go to make the standard library faster. And eventually that just became too much of a headache to maintain, so we swapped it out for this algorithm called RC4, which very soon we decided was just not secure enough to handle. So we dropped it from Cloudflare's security offerings, and then we were left with a dilemma. So RC4 is not safe, but we can't do Railgun. What do we do? Well, luckily, we have this guy. This is Vlad Krasnov. We like to joke at Cloudflare that you have different optimization levels. You can go -0, -01, like in C. Well, the highest optimization level we found is -0 Vlad. And so he's an assembly master. So essentially, he wrote AES GCM in assembly, and and it's actually now made it into the Go master, so it's going to be there in time for Go 1.6. And yeah, I didn't even show you guys the numbers yet. This is the amazing part. So the speed up is incredible. Actually, compared to the native Go implementation, it was over 20 times faster in almost every situation. So now if you use the Go standard library for AES-GCM, which is really considered to be the only secure cipher, it's going to be blazing fast. It's going to be as fast as OpenSSL. In fact, this is the same code that he got into OpenSSL. So yeah, and it's really kind of easy if you guys haven't done the assembly options for Go. I'm not going to show you the assembly, obviously. That's quite a mess to look at, but it's really easy to switch on. You have these .s files, and these have your assembly, and you just look at this function. If it enables, then you run the assembly version. So along with that, JGC passed it on to, where is he? He's over there, Daniel Morsing. Daniel Morsing worked on Railgun for a while, and we added the AES-GCM. It got into Pass 1.5. We also did some other things using elliptic curves for certificates. And one point there that's interesting to note is use CSRs. So anybody who's had to buy certificates or deal with CAs in general knows that a certificate signing request is this thing you have to create to send to the CA to get your certificate. So to actually encrypt things in Railgun, you need certificates on both sides. Only on one side, but I mean, we use it on both sides. And to actually turn that into a certificate, this leads us to the next project, which is CFSSL. So this is something that was started actually around the same time, if you can believe it, back around Go 1.0, but it's a fully featured CA, and it also does things like bundle chains and configuration scanning. This is how Railgun gets its keys. So if you have a Railgun server sitting somewhere, it goes through the CloudFlare API and sends your CSR and gets back a signed certificate. And you can go from there. I mentioned certificate bundling. This is something that if you have a website, it's really annoying to find what your chain of intermediates are. So if you have one certificate, say for example the Cloudflare's certificate, you can either build a long chain that goes all the way down to one root that may be trusted by more browsers, or you can use a better chain that uses all kind of modern cryptography, and this tool lets you do that. And it also lets you, if you want to, PKI all sorts of services inside your operation. So Cloudflare uses this for database servers, API servers, to get certificates signed by an internal certificate authority. So as this interacts with Go Crypto, you can look right here, we added ECDSA support in X509, that made it into 1.2. We also added CSR support, which I said was needed for Railgun. And the interesting thing about that was this was actually done by Kyle Isom during his interview. So when he came into Cloudflare, we're like, okay, you've got a day, let's implement a feature. And it actually made it into the Go standard library, which was really good. But over time, there were some other features that were introduced in the Go standard library that we actually saw and were kind of inspired by, and one of which is this signer interface. So this is something new in Go 1.4. It allows you to have an abstract, sort of opaque private key. As long as you can implement this interface, which the RSA and ECDSA keys do, you can basically do crypto with it, which was very important for, say, if you wanted to use hardware to store your private keys. So PKCS11, this is a protocol that is used for hardware security modules, basically smart cards, chips, anything in which you don't want to have the private key in memory or on disk. You want to have it in a piece of hardware. And in CFSSL, there's this implementation of PKCS11 key, which you don't really have to read this code, but essentially this implements the signer operation. So with this support, we were able to add PKCS11 support for our CA, and in doing so, the Let's Encrypt project, which is a new project that's supposed to come out by the end of the year to give free certificates for websites, is actually using CFSSL as the core for their CA because of this very easy PKCS11 support. So crypto signer interface was a pretty good advance. So crypto signer was also useful in another tool, and Filippo actually mentioned this earlier, and it's called RRDNS. And this is Cloudflare's DNS server. And the reason it's called RRDNS is because the developer who originally worked on it, his name was Ray Bajani, but for some weird quirk, his middle name was also Ray. So it's Ray DNS, and that's just one of our legacies. So in any case, it also started back in the early days, in 2012. And now, this is actually a year old, this stats. This website, Cloud Harmony, stopped posting stats, but it's larger than this now. This is of all the Alexa top 10,000 sites, the authoritative DNS server is RRDNS, which is in pure Go. And yeah, so this is pretty impressive. One thing, we've had DNS running for a while, and as a security company, we got to thinking, how safe is this? And there are some questions about the safety, the security of DNS, and one is this classic cache poisoning attack. This is the Kaminsky attack, where DNS is a protocol that works over UDP. So there is no IP authentication that goes on. You just get a packet in, and then you trust who it belongs to and answer it. So Kaminsky found this way to just poison DNS results. And it just, in general, if you think of an attacker or somebody who has a privileged network position, they can man in the middle and change any of your DNS requests. So one solution to this, and this is also very controversial, but very interesting, is DNSSEC. Essentially, it's digital signatures on DNS records. And it's been attempted in a number of different ways, and it's been hard to implement in the current tools, but with RRDNS and Go's filter model, or RRDNS's filter model in Go, we were able to come up with a way to safely and quickly do this. And it basically requires live signing answers. So traditional DNSSEC, you take all of your DNS answers and you sign them and then ship them out to your DNS server. In this case, you can actually do signatures at the edge, right where your DNS server is. And what allows this to actually work and scale and not break the internet is elliptic curve keys. So elliptic curves, I kind of alluded to this earlier, but they're smaller than RSA keys. They're kind of smaller asymmetric keys. And they make it so that DNSSEC is not so crappy. But the problem here is, again, live signing answers. And crypto is expensive. And so we brought out our tool, which is Vlad the compiler again. So he took P256, this is the most popular elliptic curve. This is, yes, by NIST. And this is something that he did, and he took it, implemented it in assembly inside of Go, and we submitted a patch. There's some sort of copyright issues right now with Intel that we're working through, but essentially made ECDSA 20 to 30 times faster than it was before. So Dasho Vlad to the rescue again for us on this case. So this is the timeline of the history of RRDNS, and there's Filippo time right there. He took it over around 2014, and yeah, we're launching DNSSEC very, very soon. Filippo, when? 2 weeks, yeah. So according to Filippo, 2 weeks. So this is something, it's actually been live in production for quite a while for beta customers. But again, using the crypto standard library and the crypto.signer interface. Now, this interface also was pretty interesting to us because it hinted at another project we've been working on for a while, which is keyless SSL. Now, keyless SSL is this project that we made that allows customers to use Cloudflare as the termination point of their TLS, but not to actually share the private keys with Cloudflare. They can they can share the certificates with us because that's public, but the private keys they can keep in their backend wherever they want in an HSM. But it allows Cloudflare to kind of terminate the connection and do all the magic caching and stuff like this. So I don't know if anybody's super familiar with the TLS handshake, but there's several things that go back and forth, and the private key is only really used once. So if you take that private key part and extract it out to a remote server, then voila, you basically, this is what keyless SSL is. And it gives you some good performance benefits, like rather than having to do 4 times a round trip between a client in Ireland and a web server in, say, California, you can connect to a server in, I guess that's the Netherlands, I guess, and so the client could be. In any case, there's a lot less distance to travel, so your handshake's going to be faster, and you also don't have to have the key. You don't have to give it to the third party. So we originally wrote this key server in C, and it was a nice sort of reference implementation. But around the time the crypto signer interface came out, we thought to ourselves, this is actually a perfect use case for Go and for Go's crypto library. So as you can see here, there's one step where this private key is used. In most TLS handshakes, it's a digital signature. So the signer interface is the right thing to use. But every once in a while, for older clients, this has to be a private key decryption. So we essentially needed a new interface, and that's what we brought. So this is the decryptor interface. It's pretty much identical to the signer interface in that you can take any sort of private key that can do a decryption, and it implements this interface. And you can actually take this and throw it into TLS. So if you look at in the TLS package, there's the certificate struct, and private key, crypto private key is an empty interface. So if you use something in there that implements either signer or signer and decryptor, now in Go 1.5, you can do TLS with it. So to connect that to what I'm talking about for keyless SSL is this implementation is a remote call. So this is not necessarily like a gRPC, but this private key operation, which is sign this or decrypt this, actually is just a function that does a call to a remote server to do it. And it fits in really nicely with all the rest of the crypto library. But again, we had an issue, which is with RSA. It's kind of slow, and I mean, you've seen this before, right? We got Vlad back in the game. So so now, and this one made it into Go 1.5. So there's an assembly implementation of RSA for which it's over 50% faster. This one's not as impressive as 20x, but you can take what you get. So in any case, crypto's a lot faster, thanks to Vlad. In summary, for Go 1.5, there's several new things that CloudFlare kind of gave back to the Go standard library, and that's taking these interfaces for keys and putting them into things like X509 and TLS so that you can use them in a sort of wider use case. We also implemented a new cipher. There were no 256-bit ciphers. There is now, and the faster RSA operations. So Haven time, that's Jacob Haven, who actually implemented and contributed a lot of these changes. And they've gotten into Go for 1.5. So now what's possible? Well, you can do a TLS load balancer that has a hardware key in Go, and it just works. And this is either an HSM, and coming soon we have an implementation that does this with your sort of run-of-the-mill $30 TPMs. So if you want to have secure communication where the keys are never in software or in memory, this can now happen in Go, which is really great. And not only that, you can, if you are, so I don't recommend this, but if you're not Vlad, I don't recommend this, but like if you're a dabbler in implementing implementations, yeah, you can use your own RSA or ECD implementations, and they'll just work in TLS. So as Go has grown, CloudFlare has grown as well, and there's been a lot of cross-mixing of technologies. And in summary, we love the Go crypto library, and hopefully they love us. And yeah, that's the end of my talk. So thanks.
Awesome. Thank you very much, Nick.